Yes, today we have a speaker, Feng from the University of Utah, who will give us a talk. I think he's a bachelor degree in the 1984 from Chengdu University, and then later he got his PhD degree in 1990 in the Virginia Commonwealth University in chemistry physics. He's currently a distinguished Ivan Fielder Chair Professor in the Department of Material Science in the University of Utah. He's also a recipient of 2023 American Physical Society Davidson Grammar Prize in Surface Physics. Also a fellow of APS. You have a lot of publications. I know you have more than 68 ERL publications.
Oh, 70 something. Yeah.
70 now. In my supply, you also have like 10 patents or something. Yeah. So you are actually a theorist. So theoretical modeling and computer simulations for the electronic models. So it's interesting you can pattern like you are doing.
Yeah, I did a few years experiments when I started a couple of companies for this.
Okay, so today we will hear the talks about the Excitonic Bose Einstein condensations and about the roles of flat bands on this discover this BSE phenomenon.
Yes. So, thank you. I'm good. Yeah. Thank you for the very nice introduction, and also thank the theoretical science visiting program to give me this opportunity to visit this beautiful campus. I think my experience will be wonderful. So today I'm going to discuss some of the very recent work we did on related to the flat bands, and as you can see, I added 2 words here in the title from the advertised abstract called yin-yang flat band, which I will explain. So basically, I will give a brief introduction first about what basic ideas about the Bose-Einstein concept of Bose-Einstein condensation. Then I will introduce something called excitonic insulator, many-body quantum states that with a superfluidity. And then I will introduce what are yin-yang flat bands. And then I will talk about some real calculation results. These are single exciton calculations and many-exciton calculation results that showing the exciton condensate. Then I will conclude. So briefly, what is the Bose-Einstein condensation? Basically, we have 2 basic type of particles, bosons and fermions, and for bosons, we know that they can condensate in one, due to many-body quantum states, they can have a condensation states that all the bosons occupy in the same ground state level with coherence. And this can be made analogy for something more familiar to people like superconductivity, which I will show you. And then there's a critical transition temperature for the non-interacting bosons. It's proportional to the density of bosons and inversely proportional to the mass. Experimentally, the first experimental observation of the Bose-Einstein condensation BEC is in the ultra-cold so-called cold atom lattices, and as we show here, these are extremely low temperature. This is called nanokelvin temperature. You can see below the transition temperature Tc, you can see the velocity distribution function diverges, indicating all the particles just flow without resistance, called superfluid. And this Tc, as I mentioned, is very low. And as I mentioned, one way to understand this phenomena, you can make an analogy to superconductivity. It's basically a superfluid of Cooper pairs or condensation of Cooper pairs instead of bosons. And conventionally we have a so-called BCS theory to explain the superconductivity. Now, what I'm going to talk about today is called exciton BEC. That means exciton is, so I briefly introduce excitons. So in a semiconductor, we know there's a valence and a conduction band. Now, if you shine a light and you excite electrons from the valence to the conduction band, you form an electron hole pair. This whole pair we call excitons as a new quasi-particle. And normally these excitons are metal stable. What that means is that you have to shine a light to excite for them to form. Therefore, the formation energy is positive, and then the binding energy of excitons is usually always smaller than the band gap of a semiconductor. So this indicates, like we show here experimentally, if you do the absorption spectra, this is the band edge, and the peak is always below the edge, and this gives you the formation energy of excitons. Now, there's a theoretical proposal very long time ago in the early 60s that shows a special, very exotic behavior excitons. That is, this excitons formation become negative, or the binding energy of excitons exceeds the band gap. Thus induce so-called excitonic instability. That means exciton can spontaneously form without photoexcitation. And under this condition, there's some classical pioneer work by Maud and Feng, for example, very famous series. They show that you can start with either semi-metal, and then you excite, you condense it, you lower the temperature below the critical transition temperature. These excitons form spontaneously, open a band gap that is very like to analogy to form the Cooper pairs for superconductivity. So you can use exactly formally the same BCS type of theory to describe this transition. And or you can go to a stronger limit where you start from a narrow gap semiconductor, and these preformed excitons, if they have a negative formation energy, they can condensate. And this is more close to the classical BEC type of transition. So there's a crossover from BCS type to BEC type of condensation, which is also a hot topic in non-conventional superconductivity currently. Now, however, we know there's a lot of research and very nice observation experimentally to see the superconductivity, but hardly you can see any experiments on EI, so-called excitonic insulated states. And one of the challenges is these excitons are neutral spaces, because you have an electron positive, negative charge, and the holes are positive charge. The electron hole pair has no charge. So even the superfluid without resistivity, you cannot observe it. And normally, people, for now, many work has been done by measuring this gap opening, just like a superconducting gap opening with a function as a function of temperature, as I show this plot. But this can be ambiguous, because there are many other transition can also induce the so-called metal to semiconductor transition, including structural transition can induce such kind of transition. So now one way to overcome that challenge, I will introduce excitons in the spin states of excitons. So basically, if we consider the spin of electrons and holes, then you can have a singlet versus triplet excitons. Basically, if the holes and electron have opposite spin, then the total spin is 0, we call it singlet. Or they are lying in the same direction, spin 1, we call triplet states. Okay. Now, by exchange interaction, usually the triplet states has a lower energy, and so there's something called intersystem crossing. Basically, this singlet is dark, is bright, and the triplet is dark. So when you forcibly excite the singlet, they can transfer by intersystem crossing to form a triplet because they have a lower energy. And this actually is a very hot topic in organic spintronics and organic photovoltaics, because it can enhance the solar cell efficiency by this transition. On the other hand, for our interest here, the triplet excitonic insulated states, if they are condensate, then you have a so-called spin superfluidity because the charge is neutral, but they have spin flow. Yeah, so this will be a very exotic and interesting phenomenon to be observed. So to form this very exotic state called excitonic insulated states, you can see we need to reach this very challenging condition that the exciton binding energy has to exceed the band gap. In other words, the condition for this to happen, you can imagine that you need to reduce the screening of electron interaction or Coulomb interaction in a material, so that the binding energy increases, and also you need a small band gap material so that this condition can be fulfilled. Now, what's the condition to realize this condition is usually you need a low dimensional material because, for example, in a 2D material, the screening is greatly reduced because if you have a single sheet, then the electromagnetic field can go outside the vacuum without being screened, right? And another condition is, as I mentioned, you want a small band gap material. But if you look at this, the polarizability or the dielectric constant of a material, this formula shows that is inversely proportional to the band gap. Therefore, if you look for a small gap material, this goes up, and then the screening goes up. It's not good. Therefore, you want this numerator to this denominator. You want this numerator to be small. This is basically the transition element, matrix element between the conduction band and the valence band. So you want the band edge absorption to be very small. And another condition is you want to enhance the electron hole overlap. The wave function of electron holes, you want them highly overlap, so therefore the screening is reduced. And finally, if you prefer the triplet EI states, which, as I mentioned, for spin superfluidity, you want to enhance the spin splitting, that is the energy difference between triplet and singlet. So now I'm going to introduce band structure because, as I said at the beginning, you have a flat band, right? So normally, if you consider the band dispersion, they can have three kinds. So most common material have this normal band dispersion, that is parabolic, like semiconductor condensation and conduction and the valence band, where the energy is proportional to the momentum squared, parabolic. And then you can use effective mass theory. So that means the electrons in a solid is essentially a free electron with a different mass. And in this sense, we are talking about basically single particle physics. Now, there are two types of exotic band structure. One of them very familiar with these days after the discovery of graphene. So it's basically called the Dirac electrons, where this energy is proportional to momentum. So it's a linear dispersion. And this one gives you an effective mass of 0 because these electrons, quasi-particles, behave like photons. Okay. So initially, this is called the Dirac equation because basically Dirac equation is derived from Schilling equation by considering the relativity effect or spin-orbit coupling effect. So this is a single particle plus relativity effect. Now, if you move mathematically, you can imagine if I move down further, instead of go to the k squared to the k1 power, I go to k to the 0th power, then my band will be flat. Okay, this is called a flat band. And then the mass, the effective mass of this particle go to another extreme to infinity. And in this case, that means the electron kinetic energy of electrons are diminution. Therefore, very tiny bit of Coulomb interaction become magnified, super strong. So this is inherently we call it strongly correlated system because the Coulomb interaction dominates the transport property of electrons or physical behavior of electrons. So now in the last 2 decades also, people also discover so-called from the topological insulator to topological materials, discover that this band also have band topology instead of to band dispersion. So correspondingly with these 3 types of bands, one is, as I mentioned, the conventional gapped material like semiconductor, if the band gap is the band is inverted around the band gap by spin-orbit coupling, then we call this topological insulators. Okay, and if you consider the Dirac band, actually Dirac band is a topological semi-metal, and this Dirac point is basically a Berry flex center, or Berry phase means the electron wave function have a phase factor, and this exhibit so-called Carroll anomaly, means there's no magnetism, but they can have magnetic response due to the Berry phase. Now, another case is a topological flat band is also topological. And one way to simply see this is that this flat band is very similar to the initial discovery of quantum Hall effect, where basically you have a 2D electron gas, you apply a perpendicular magnetic field, you form Landau levels. So these Landau levels is just like a flat band, okay? And actually the initial concept of topology introduced to the condensed matter community of material physics community is by explaining the quantum Hall effect using the band topology or Landau level topology. So these are topological because they are in analogy to Landau levels. And I will discuss more some other properties of topology related to compact localized states. Okay, so now just imagine that we have two flat bands, and here I introduce the name of yin-yang flat bands. Basically means the band has a different chain number or different topological index. One is chain number -1, and another one is chain number +1. Then you imagine you form excitons, you excite electrons, or some way the electron spontaneously forms. Then this excitonic quantum states will be very exotic. So we ask question, what happens if this happens? But before, yeah.
C -2, would you have similar kind of excitonic insulator?
C is the chain number, yeah. Topological number.
It will not +-1, something different.
1
+1 and -2.
Oh, that's a very good question. I don't think people can answer that question yet. I'm no one in. So I will answer you that question later. Okay, try. So now I will give you some recent work how we construct a band structure like that with two flat bands, right? So let's use the very simple lattice model construction of bands to understand the process. So if we consider graphene lattice with a honeycomb hexagonal lattice, that's the simplest case people know. If you consider only nearest label hopping T, the single electron Hamiltonian is very simple, just hopping terms T, and then this Hamiltonian is with 2 atoms per unit cell. It's 2 by 2 matrix, give you 2 bands. That is so-called Dirac bands. Okay, so that's very easy to do a tight banding model. You solve that for. Now, one thing I want to point out here is that the graphene is also called something called bipartite lattice. That basically means this lattice have 2 sublattices of A and B, and by bipartite, the condition is that you only allow A-B hopping, that means inter-lattice hopping, but you disallow AA or BB hopping, the intra-lattice hopping, which here will be the secondary hopping. So that means you only including this T term, then you will guarantee this bipartite lattice guarantee chiral symmetry. So what that means that the bands always have a so-called particle Hall symmetry. That means you have a positive E branch and the negative E branch mirror to each other. So at every K point, you have plus E eigenvalue, you have a minus E eigenvalue. So that's the chiral symmetry. Okay. Now, another very well-known lattice model we call the Kagome lattice. So the Kagome lattice look like this with 3 atoms per unit cell. Therefore, if you again consider this nearest label hopping tight banding Hamiltonian, you have 3 bands. So in addition to the 2 Dirac band I just showed you before last slide, there's addition of flat band. Okay, if you do a tight banding calculation, this can be easily shown. Okay, and this is a chiral band structure because this is not a bipartite lattice, obviously with 3 atoms per unit cell. Now, one interesting observation is that if you change the sign of this T hopping to minus, it's essentially the -1 is e to the I pi. Basically means you add a phase of pi to the hopping, to the electron wave function of hopping. Then this flat band move on to the top. Okay, that's also an indication of the topology of the flat band, or the two flat band have opposite chain numbers. So now, why this Kagome lattice have this kind of totally flat band? And actually, there's a mathematical theorem worked out a long time ago. Basically, called the line graph theorem. It's a graph theorem. The line graph theorem basically said I start with a root graph like a graphene lattice or hexagonal lattice, and now I'm going to construct a line graph. How am I going to do that? Is you basically this graph consists of vertices and edges, as I show you here, and then I choose the edge center. And when two edge centers share a common vertex, I make another edge. Okay, now I will take away the root graph. I arrive at the Kagome lattice. So Kagome lattice is a line graph of hexagonal lattice. Okay, then the powerful mathematical theorem states that if you have an infinite lattice, you construct line graph, it always have a flat band. Mathematically, graph theorem confirms that. So the spectra of infinite line graph, the eigenvalue of adjacent matrix. Adjacent matrix, in this case, is just Lewis hopping in tight binding model, and always have one eigenvalue at -2 with infinite multiplicity. In physics, we call it degeneracy. So, okay. So this theorem gives you guaranteed flat band in a lattice. Now, how I'm going to construct this so-called yin-yang flat band? You can imagine I have a T, hopping T larger than 0 with flat band at the bottom, smaller 0 than the flat band on top. If I imagine I can put them together, I will have a yin-yang flat band, right? So how am I going to do that? The immediate way, intuitively, when we start at the beginning is that let's just consider diatomic Kagome lattice. So that means on each Kagome lattice side, I put 2 atoms instead of 1, because I know Kagome lattice is guaranteed with 1 flat band. So in that sense, my band structure will depend on these T1, T3 hoppings. So I can construct a band phase diagram that basically in the parameter space of hopping. So for different value of T2, T3, you can see I can get different type of bands. And one of the region I can get is this 2 flat band at the Fermi level. So that's cool. So actually, this ideal in a flat band can be formed at a so-called chiral limit, which is, I mentioned the chiral symmetry is guaranteed by bipartite lattice, just like a graphene lattice. And so in this case, I will have a bipartite diatomic Kagome lattice, means that I have to eliminate all the intralattice hopping, allow only interlattice hopping. In this case, it will be only allow AB hopping, but not allow AA and BB hopping, which is T2. So if you set the T2 equal to 0, then this is the band structure you will get. So it's ideal yin-yang flat band or 2 set of Kagome bands with opposite hopping signs. So this is a 3D plot. And I always say this is the most beautiful and rich band structure I have ever seen. And I will show you how rich and how beautiful they are. So as I mentioned, initially, we only by intuition, we figured out this yin-yang flat band. And until early this year, we published a paper that we worked out also a graph theorem for the existence of yin-yang flat bands. Basically, in the graph theorem, there's a construction called a bipartite double cover. Basically, you split a graph like this Kagome lattice, this black dot, split them each dot into 2, and then you only allow inter-sublattice hopping, just I showed you before. So this theorem basically says the BDC, which is the bipartite double cover of a line graph, will always contain 2 flat bands at -2 and 2 energy. Okay, why I call it yin-yang flat bands? One way to directly see this is that if you add a spin of the coupling to this band structure, you can then calculate the chain number for each spin channel of these bands and spin chain number. And then you can see I can plot the barrier curvature within 2 flat band. And these white and the dark color shows the sign of the barrier curvature. Basically, is a chirality. That means one band is left-handed, the other band will be right-handed. Okay, so that's a chiral symmetric and limited yin-yang flat band, because it's very like the yin-yang diagram in Daoism in China. So actually, the funny story, when we published this paper, the editor finally said, could you remove the yin-yang from title, but I can keep it everywhere else because no one knows what they are talking about. Anyway, so that's what happens in the paper we published. Okay, now there's something peculiar. It's hard to do. Is I go back to this slides and maybe quickly here is that this chiral symmetry requires T2 equal to 0, but T2 is the secondary label, while T3 is a third. So that means I keep T1 and T3, eliminate T2. That sounds very unphysical because the shorter distance hopping is gone and the longer distance you keep it. Why? How can that happen? So in this case, we also accidentally found a way to do that. Is that at that time we didn't know about the yin-yang flat band. We just interested in the patterning graphene into super lattice. We called superatomic graphene. Basically, drill holes in graphene, or you make this as a molecule, a triangulating molecule, and you stack them into a hexagonal lattice. So instead of a graphene with each lattice with one atom, you now replace a single carbon with 3 benzene rings, and you form a hexagonal lattice. If you do that, you do the band strike calculation, it's exactly a Dirac band, very same like a graphene. Now, if you make this super atom molecule larger with 3 rings and 6 rings together, then your band structure evolves into this shape. Now you increase further 4, then you form this 2 flat band. So why is that? That is because if you consider this as a super atom or as a molecule, there's a frontier molecule orbital that like a homo-lumo level of molecule. Then you look at the symmetry of those orbitals, you find at this small size, the frontier orbital is asymmetric. So this whole thing molecule behave with one orbital like graphene PZ orbital, so you form Dirac band. Now, if you increase the size, that frontier orbital become PXPY type. Then you form 4 bands because the 2 atoms each has 2 orbitals at the Fermi level. And this is basically a PXPY orbital in a hexagonal lattice. It's well known to have this kind of band structure. Now, if you add one more atom, actually the frontier orbital become SPXPY or SP2 type. Then they become like this, then you have this. So to quickly, so if you have SP, yes?
Why in the last, on the right, you lost plus minus symmetry?
No, this is that means the T2 is not exactly 0 in this real material, but close to be. This is already a real material, not a model anymore. Yeah. So, but the reason for this to happen, T2 equal to 0, is that if you consider 3 orbitals, SPXPY, actually we can do the flat band gamma point wave function plot to show the S and PXPY symmetry. You can see you form SP2, then this basis, the T2 is basically the hopping between the 3 bases. So by also normal condition of bases is 0, also orthogonal to each other. But the T1 is just hopping between this sigma bond and the T3. Yeah. So that fulfills this very strict condition that T2 is 0. So with this material that can give us the yin-yang flat band, now we proceed to say we can do calculation to show exciton behavior, because we, as I imagined at the beginning, the excitonic behavior should be very strange, right? So let's do it. So what we're going to do is we will use this, we call it line by line, because this have a line, the side has a line size. Superatomic graphene, also in chemistry called triangulating 4, because there are 4 benzene rings on the edge. And you can calculate band structure for this real material. As I showed earlier, it indeed has a yin-yang flat band. The bandwidth is slightly different. We just discussed because the hopping condition is not ideal, but very close to be ideal. And then, of course, as I mentioned, in order to reduce the screening for Coulomb interaction to enhance the binding energy of excitons, we want a 2D material with small gap. So this is indeed confirmed that condition. And then we also want the band edge absorption to be small because that can reduce the band edge hopping to reduce the polarizability or dielectric constant of a material. And for the flat band, this hopping terms actually is inverse proportional to mu, which is effective mass. For flat band, it has almost infinite effective mass. So this 1 to 1 bar, 1 prime transition is almost none, and the other transition have final absorption. So so we have a diminishing band edge transition between two flat bands. And another one is I mentioned that flat band is formed by so-called destructive quantum interference. What that means? It's basically a phase cancellation. So if you calculate the flat band wave function, then you do a Fourier transform into real space. So this is the lattice of diatomic Kagome lattice I showed earlier. And you can see this flat band wave function is totally localized on this plaquette. And the sign red means this nodal sign of this wave function is positive, and this is negative. So this function is totally localized and also have a net zero hopping outward. Because if you look at all these nearest label side of this wave function plaquette states, they cannot hop out because the positive and negative sign can phase cancel out. So as though this T is finite, but the net hopping is zero, no matter how big the T is. So that's called destructive interference, or they form so-called compact localized states. Now, this is the conduction flat band. If you look at the valence flat band, the shape is slightly different. No, the distribution of node is different, but the condition is fulfilled. It's all cannot hop out, and the net hopping is zero. So for this reason, you have enhanced electron hole wave function overlap because they are very localized, similar size and shape. So I will skip this. Then what are you going to do is first thing we want to calculate is the exciton binding energy. So you can do DFT-GW calculation. I will skip these details. And then so first we will do a band gap correction. We know the DFT is underestimating the band gap a lot. In this case, the underestimation is very huge. Because the system had a so small screening possibly. And you can see the gap increase to about 1 eV. Now, after that, we can do the exciton calculations. So here I will show you the BSE calculation of excitons. I show both the singlet with electron and hole spin opposite to each other, and the triplet states. And I plot these both plot as the density of states because this triplet is stuck, so they don't have absorption spectra. But for singlet, this is essentially the same as the absorption spectra. So you can see for singlet, the binding energy of this singlet exciton is 0.7 EV. Remember, the gap is about 1 EV. So the formation energy is still positive, but this binding energy is very strong. There's a lot of research in transition metal dichalcogenide of excitons, basically because they have a large binding energy, long lifetime, which is comparable value to this showing here. But even more interestingly, and now if we look at the triplet, we find these peaks are below this zero. That means the exciton has a negative formation energy, so they can be spontaneously formed by lowering the temperature in this quantum states. Okay. Due to the interaction, many-body interaction. And the reason for why these two excitons behave differently, as I mentioned earlier, we can also check the exciton wave function. So here for singlet, you can see it's actually much more diffuse, while for triplet, it's much more localized. Therefore, the electron hole wave function overlap is even bigger. Therefore, the screening is even more reduced. So with that singlet calculation, I want to just comment that many DFT calculation, when they make the prediction on excitonic insulated states, they stop here because it's very hard to do multi-exciton density function or GW calculation these days. So many people just say, oh, I predict a prediction is that I have a excitonic insulator states, and potentially excitonic Bose Einstein condensation. However, to really confirm that for exciton Bose Einstein condensation, actually you have to do the multi-exciton calculation, which my graduate student said at that time, spent 2 more years after publishing that paper, did the second work. So for multi-exciton calculation, mostly we are interested, first of all, what's the formation energy? We show that formation energy has to be elective, right? So, but if you have more exciton form, they interact. Is that still to be elective? And also how they interact. Secondly, we want to show quantum coherence for the condensation states, which I will show you how to do that. So for doing this, as I mentioned, it's not possible to do GW calculation these days yet. So we will switch the method to something called exact diagonalization method to exactly diagonalize a tight bending Hamiltonian with extended Hubble model. So first of all, we will consider this single particle band structure, which is described by single particle Hamiltonian, and then we can fit these coefficients of hopping to the band structure. So by fitting this, you can see this tight bending dashed line agrees with this red solid line perfectly obtained from GW calculation. Then we will consider this Hubble term with interaction terms, which we treat up by parameterizing using the screened Coulomb potential. And then we fit these results by calculating the exciton, single exciton properties. So for that, I just show you how complex this calculation is. So if you consider the exciton interaction, which have electron-electron interaction, hole-hole interaction, electron-hole interaction, you have Coulomb interaction, you have exchange interaction. So this terms goes up. And then I was amazed by my student in that sense. Basically, if you go to by system size means the lattice size, the exact diagonalization, the matrix size is 10 to the 12 times 10 to the 12. Okay, so that's a huge amount, humongous matrix you diagonalize, and which is the space, Hilbert space dimension. Okay, now as I mentioned, so what we're going to do is we calculated this single exciton for both singlet and triplet properties. One is their binding energy, and then the exciton wave function. So now we try to match this tight bending exact diagonalization method to the GW results for single exciton, and by tuning these Coulomb interaction parameters. So we succeeded doing that, and they have a very, very good agreement. And after that, you can use this tight bending ED method to do many excitons. So now I'm going to solve the many-exciton wave function problem. First, let's check the formation energy. Okay, in a coherent state, like a BSE state of superfluid flow without dissipation, then you essentially the particle distribution is boson distribution, means there are no interaction, totally random. Right? And so amazingly, that's what we found. So when we calculate the average formation energy per exciton, basically we calculate the total exciton formation as a function of EP, means electron population. So you increase the population of electrons in the lattice. You can see this average formation energy constant. So excitons behave as if there's no interaction. This is very amazing because, as I said, there are so many interactions, so many particles, Coulomb interaction, right? But the net results is almost there's no interaction. And then we will check the coherence. And this one we borrow some methodology developed a long time ago by Penrose, Onsack, etc. And in this review article by yin-yang, basically you calculate something called off-diagonal long-range order that can show you the quantum phase of coherence. For example, here the review is about the liquid helium and the superconductivity. As I mentioned before, the BSE and the superconductivity has a analogy to be made. And specifically, you calculate the exciton two-body density matrix. If this matrix have a single large eigenvalue, that means all the occupation of all the, that means all the particles condensate on the same quantum states or occupation of one state. So indeed, we found that you calculate this two-body density matrix. You diagonalize it, the eigenvalue has only one peak, and the rest is very small. So that indicative of excitonic Bose Einstein condensation. And then we can check what's the role the flat band played in this condensation. So what you're going to do is I can tune my calculation parameter. I can make this conduction band parabolic instead of flat. Okay, and then I can repeat all my calculations for excitons. And you can see for now, the average exciton formation energy is no longer constant, and it goes up with the population of excitons. So indicate there's a very strong exciton repulsion. And furthermore, if now you calculate the two density matrix, eigenvalue of two density matrix, there's no off-diagonal long range order because you don't have a single peak anymore. So furthermore, and as I said, we still want to show how this exciton behaves. As I mentioned before, that there's something called a BCS BEC crossover. Basically, what that means is, in a very intuitive or layman's term, is excitons are composite bosons. So there's an electron hole pair, right? So it's a two-body. But if their attraction is so strong, they behave like point-like bosons. Okay, point-like boson. Then we call it BCS to BEC crossover. Does that make sense? So if it's point-like bosons, then it's just like half sphere and no interaction. Then this BEC states can be easily constructed from a single boson wave function by the nth power and normalized. So then this is the ideal theoretical BEC state of point-like bosons, which we calculated from single boson wave function. Then we can solve the many-exciton, a single exciton wave function. Then we can solve the many-exciton wave function by exact diagonalization method, which is the exact, this wave function. So we do a dot product of this ideal point-like boson many-body wave function with our solution. If this overlap is 1, that means our solution is like a point-like bosons. Otherwise, it's not. So you can see the example I showed you for our real material, superatomic graphene, and we show the off-diagonal long-range order for BEC state, but this overlap is not 1. So what we are going to do is we will do another parameter tuning. We make this flat band gap between two flat bands artificially small, so that the exciton formation is mostly dominated by these two flat bands. Then you can see this very close to 1. So that means these flat bands can promote excitonic BCS to BEC crossover, because by contribution of exciton flat band to the exciton formation, increase this contribution, you can make the excitons more and more point-like bosons. Okay, I'm almost done. So in summary, I basically showed you 2 results. One is by density functional theory GW calculations, we can calculate a single exciton formation energy. And we show how to do this by the construction of yin-yang flat bands. And this elective single exciton formation energy is indicative of excitonic insulator states, because in making this negative formation energy, flat band can significantly reduce the screening for exciton formation. And this is the first paper. The second paper, we discussed the multi-exciton formation energy. We further show that this negative exciton formation energy is only a prerequisite, but an insufficient condition. That means although exciton can spontaneously form with the negative formation energy, they're not necessarily condensate with quantum coherence. To show quantum coherence, you have to show the off-diagonal long-range order, and we show that flat band can enhance this quantum coherency, promote BCS to BEC crossover. And to summarize, as I mentioned, this band structure. So for all the devices we have used today, computers, cell phones, all the electronic or optoelectronic device is based on the band theory in essence. And in that context, I will name something called a quantum semiconductor with yin-yang flat band edges. So conventional semiconductor, as I said earlier, you have these parabolic bands, right? Then the flat band semiconductor or quantum semiconductor have a flat band edges. And in this case, the carriers, the transport carriers are single electron device or effective mass theory. And in this case, however, the transport is dominated by correlation or electron-electron interaction effects. So the so-called quantum materials or quantum is basically characterized with two properties, that is topology and interaction or correlation. So flat band covers both in that context. And currently, for example, we're studying how you dope this. If you dope a quantum semiconductor, what happens by impurity? So that means the flat band will be partially occupied. There's the spontaneous instability of quantum phase transition. Another comment is that after our theoretical work, there's a group at Berkeley actually made the sample of this superatomic graphene trigonine 4 lattice. These are some experimental images. You can see these materials are not made perfect, but they already observed some very interesting phenomena like BCS, which they use the BCS type of condensation theory, very similar to theoretical work we did to explain what they see. Finally, I just show that many things we can do with these two yin-yang flat bands as a new quantum semiconductor. And so there's a short list of many. And also, you can imagine there are many other topics can be very interesting with yin-yang flat band, such as artificial system. That means photonic lattice or other lattice. If you make two flat band, what's the physical manifestation of them there are? And finally, I want to acknowledge my graduate student, former graduate student who left the group last year for postdoc at Berkeley, who did all this work I presented today. And this work are funded by DOE. And these are collaborators and people contributed to what I talk about today. Okay, thank you.
Questions? You want to go first?
Yes.
What's the temperature dependence? Can your theory say anything about the temperature dependence?
Yes, that's a very good question. All these calculations we started so far are zero temperatures. And so we are thinking about to do time-dependent DFT, just see the single exciton dynamics in two flat bands. I think before doing many about it, I think that itself is very intriguing, but also challenging, but but a very interesting topic.
So the experiments that your collaborators did?
They are temperature, of course, final temperature measurement. I don't remember what temperature. They basically show, I don't know how, this paper is not published. So there may be some debate on the interpretation of their observation. Yeah, but these are no temperature, but not there. In other words, we don't know how to predict TC, just like you don't know how to predict the superconducting TC for high non-conventional type of superconductivity. TC is hard to be predicted.
So my question had two parts. The first part was, can you make higher Chern numbers symmetric yin-yang?
Very good question. We think
one is asymmetric, -1, +2, etc.
I don't know about the asymmetric ones, but we have idea to do the high order symmetric ones for sure. One way to do is I didn't have time to discuss is we have another paper basically called orbital design of flat band with high Chern number for one. Okay, now if you can design one high Chern number flat band, then you can use the graph theorem we developed to contract the pairs. Then you should have a pair of high Chern number. Does that make sense?
And the condensate corresponding to the higher Chern numbers will have different properties.
That's a very good question. So, in fact, in all these calculations, Taliban ED calculation, we don't take into account the chain number at all, right? Although it is chain number by default, but we don't know if it's not topological, what happens, no one knows, right? Because I only have one set of calculation with the plus or minus one chain number. I don't have the comparison results. And also another thing we are studying is I didn't have time to mention is that this band touching point with the flat band is called singular touching point with a divergent quantum metric. That means the quantum distance between electronic states are divergent. That give you a lot of physical phenomena such as anonymous non-level spreading, which we are just studied recently, and then there are topological related properties. But for exciton formation, for example, is these excitons are topological or not? We don't know yet. There can be topological excitonic states. Which you have to calculate excitonic band structure and figure it out.
I haven't checked this live yet, but so what's your viewpoint? What experiments?
Okay, very good.
What's the situation?
I think the challenge is this quality.
Okay.
You can see this, they're not crystalline enough. So what they did is that another challenge is they put this on gold substrate. So they put this molecular precursor, and then they deposit on the gold substrate, and they self-assemble into a 2D layer. But you can see some parts are perfect, right? But not all the parts are perfect. And I think that is made it a challenge to have a very good experimental data. If they can succeed to make a large area crystalline sample, it'd be wonderful. It would be very, very exciting. Because I think observing the excitonic condensation, especially observing the spin superfluidity, will be a very, very big deal. Because we have superconductivity, the charge superfluid, right? We don't have a spin superfluid, so not yet.
Do you have any inorganic candidate?
There are for yin-yang flat band it's hard, but there are some not pure inorganic. We have the proposal with the integrated organic inorganic integration. There are some candidates like that. We suggested it, but not a pure inorganic, not bulk inorganic material. But you can have 3D flat band. In the flat band in the whole 3D Boolean zone has a constant energy. That's possible. Called periclo, briclo or something material. They have a 3-dimensional flat band.
Biocloud is a direct analog of Kagome treatment.
E3D, So they can have a 3D flat band. So you can also construct a 3D line graph. In that sense, you can also construct the 3D BDC we just recently developed.
The disadvantage might be dimensionality, higher dimension.
That's very interesting. What happens if you have a 3D flat band to transport? I don't know. A 2D transport. 3D flat band, how the electron transport, I don't know. I personally, I think in that kind of 2D is more interesting, even like a quantum Hall effect. It's mostly 2D. You can have 3D quantum Hall effect, but your measurement and eventually you still go to 2D to measure it.
Nowadays, there are a bunch of Kagome
materials. A lot of interest. But I think many of them are not truly Kagome in the sense they are Fermi flat band is far away from Fermi level. They just have a Kagome lattice there. But the band of interest may not be, truly from the symmetry of Kagome lattice. They have a sublattice in many atoms. There's a sublattice is Kagome, but if you look at the band structure, it's all over the place, very messy. But the Kagome metal or Kagome material has been very hot these days. But personally, I think many of them are just ordinary, not truly related. It's a D band, it's narrow. So.
And how do we think about transport? Because the mass is also
Hey, that's a very, very good question. So yeah, so I often get these questions because they said if you have a flat band and the electron doesn't move at all because they have an infinite atomic mass. And so you are right, but you are talking about a single particle physics. So what happens to a flat band superfluidated is you consider 2 electrons in the flat band, Cooper pairs. And then when they, you can calculate the so-called superfluid weight of Cooper pairs within the flat band. Then they become finite. So yeah, in other words, each one individually cannot move. But if you consider 2 move together, then their dispersion is no longer flat. And partly due to the more profound reason, partly due to they call it the obstruction to barrier phase, because the electron wave function cannot be totally localized. So they have overlap for their Wannier function. That means they're dispersive. So yeah, so that due to topology in some sense. So the Cooper pair have finite superfluid weight, even though single electron cannot move. So very strange. Yeah. So that means due to electron interaction, they can move in a quantum coherent state collectively, but they cannot move individually like running. Yeah, it's a very good question, but there is a hard question too. That's not fully clear.
Any question from Zoom?
No. Okay.
So what is the experimental way to detect spin superfluid as
just like doing spin Hall measurements, people measure the spin current. That people can do the magnetic, right? The inverse spin Hall effect, the spin Hall effect. They can measure the spin current.
But what's the direct evidence of superfluid?
Superfluid, I mean, you measure that without the resistance, just like yeah. Yeah.
Anyway, I think this room will be for
2 o'clock. Yeah.
So let's thank the speaker again.
Thank you.